that's residual analysis. So the residual is defined as the difference between the observed and fitted value. And we talked about that. It's a deviation of between the data and the fitted data. So it's also a measure of the variability in the response variable that is not explained by the regression model. Residuals can be thought as the observed value of the model errors. So it can be expected that if there is any departure from the assumption on random errors, then it should be shown up by the residual. So the analysis of the residuals, it helps us to find out the model inadequacies. So look at here, residuals have zero mean, as like we talked about that. Expected value for our residual should be 0. Here's a proof of it. And the approximate average variance of residual is, when we want to find it, it's going to be, we talked about that before as well. So we would look at the MS of the residuals, and it's the mean square of residual. We would call it mean square of residual. It's the same as the mean square of the error. And it's here, it's the same as MSE in ANOVA. As I said, here you can have SSE. You might see that in some books they write it down, residual sum of a square RSS. It's different than SSR, sum of a square of the regression, be careful. And then divided by n minus p. Sometimes it's easier to work with scaled residual. So this is the residual, like the average variance of residual that we would have. So now we are going to talk about the 4 methods for scaling these residuals. And for scaling these residuals, the first one is standardizing the residuals. We are looking if we are using the mean square of the residual, like mean square error. In this one, you will see the residual are standardized based on the concept of the residual minus its mean and divided by the standard deviation. So when we look at it, it's like that. You would say that the standard residual, it's equal to the EI, whatever residual that you would divide it by the square root of the MSE or MS of the residual. That we will find it from the ANOVA table. And then we call it as a standard residual. We would say that the expected value of the standardized residual is 0, and the variance of the standardized of the residual, if you get the variance of this one, you will see that it's going to be almost 1. So a large value of the standardized residual, let's say greater than 3, potentially indicates an outlier. This is another method that you can find out the outlier. The next one is the studentized residual. The studentized residual is a little different. It uses the exact variance that we have for EI. The standard residual used the one that we had before, the standardized one. I said that it used the MS of the residual, but that one, the studentized, is used the exact variance. So let's look at this. Let's first find the variance of the EI in the model of the ordinary least square model that we have. Estimator y is equal to x times beta plus epsilon. We said that beta is x prime x minus 1 x times x prime y, right? And the residual vector is we would say E is equal to y minus y estimate. And then we would say instead of y estimate, we are going to write down is x of, this is beta. So it's x times beta. It's like this one. And then y, we would say, so here we defined hat matrix. Hat matrix, you can see here, hat matrix is equal to x times x prime x power minus 1 times x prime. And then it's just easier when you write it down. So you can say that, for example, you will see that at the end of this chapter, we have a, like I wrote down all of the equations, and then you will see that it's based on the hat matrix. So what we would say, we say that we can write down E, the residual vector, when we do some like playing with the mathematics behind the, like with this, when we define the hat matrix. And hat matrix is general form. It's not just that we use it here. In stats, we use it a lot. And in tutorial and practice problem, you will see that as well. So we would say that the residual is like H complement times epsilon. So this H complement is exactly the complement concept that we had in the second year stat when we were working with the Venn diagram. So when we say like I minus H, it will give you H complement. So it's like you can write an I minus H as well, and H, as I said, is equal to this one. So if we said that E is equal to H complement Y, and also is equal to H complement epsilon, so residuals are the same linear transformation of Y and epsilon. We can write down the variance of E as well. So we would say the variance of the variance of E is equal to variance of the H complement times epsilon, and H complement times variance of epsilon. It's like that. We would just try to move this one out. But at the end, we would have, that's the equation that we would use, that the variance of E is equal to, here, variance of epsilon is equal to sigma to I, and this is the equation that we had it before as well. So the matrix I minus H is symmetric, and but it's not diagonal. So residuals have different variances and they are correlated. So we would say the variance of the EI is equal to sigma 2 times 1 minus H of II, and the covariance of like two different, because we have beta, each of these betas, they're going to give us, like we can have a residual for it, right? So for the covariance of the EI and EJ, it's going to be minus sigma to H of I and J. So when you have your hat matrix, we have an example in the tutorial parts. So it's like then you will see that we have the, whatever you have in your diagonal, consider it as your like H11, H22, those ones for variance. And whatever you have like off diagonal, consider it for the covariance of that. So we can say variance estimate for EI based on this method so far. It's going to be MS of the residual times 1 minus HII. So far we said that the variance, always we said that, okay, the variance is going to be the MS of the residual, right? So based on this model, it said that mean square of the residual, in fact, overestimate the variance that we would have for the EI, which makes sense because this one, it's equal to the variance that we have for the pure error and variance that we have for the lack of fit. So it makes sense, the thing that we have here. Okay, so this is the final equation that we are going to use. So the rest it was just proving, so you don't need to, it's good that you look at it if you are interested, but this is the final equation that we would use. So the studentized residual, we show it by Ri, is EI, and for like in the denominator, instead of writing down a square root of the MS of the residual, we would write down a square root of the MS of the residual times 1 minus H II, like the hat, we would use the hat matrix. Now, maybe you have this question that, okay, so a studentized residual or a standardized residuals, when do you want to use which of them? So in many situations, the variance of residual stabilizes, particularly in the large data set, and there may be little difference between the standardized and studentized residuals, because one of them, it has the 1 minus H, right? In such cases, both residual often convey equivalent information. However, since any point with a large residual and large HII is potentially highly influential on the least square feet, so examination of a studentized residual is generally recommended. So we would prefer to consider the studentized residuals. The next one is the PRESS, and the PRESS, in fact, is the prediction error sum of squares. So SS we had it before, right? Sum of a square is error. Just know that this PR is prediction error sum of a square. So the PRESS residual are defined as observed value minus fitted value of the like ith response based off the all the observation except that ith number. So why PRESS? If y I guess outcome at I is really unusual, then the regression model based on all the observation may be overly influenced by this observation. So what that is like that when we have problem with one specific point that we need to consider it, but for the just for the residual we would prefer to remove it. In that case is that you would say, okay, I'm gonna look at the observed value minus that fitted value of the ith number. That it's like that, it's unusual. This could produce a similar fitted and observed value, and consequently E will be small. So it will be difficult to detect any outliers. The equation that we use for PRESS, the PRESS equation is that sigma y minus y estimate power 2. So it's nothing like you wouldn't see or you wouldn't expect. The only thing is that this y is like that. The difference between the y as data point and the result that you would have for the from the data, like as a prediction. And then we would say it's equal to the EI divided by 1 minus HII that we had it before. And we would say the R square of the prediction is going to be 1 minus PRESS times SS of total, because PRESS is like, it's kind of the SS of the error, right? So we said that is the prediction of error of sum of a square. So we can say that when we are talking about the R square, so far we had R square, we had adjusted R square, and this one is the R square of the prediction. We would say 1 minus the PRESS, like the amount of the error within that, like for that specific I, divided by the SS of total. For example, if the R square of the predictor or prediction is 0.89, then it indicates that the model is expected to explain about 89% of the variability in predicting new observations. So the PRESS, it helps us to find out the R square for the prediction. The last one is the R student, and it comes like this. The studentized residual is often considered as an outlier diagnostic, as we talked about that. This is referred to as internal scaling of the residual, because mean square of the residual is an internally generally estimated of sigma 2 obtained from the fitting the model to all n observation. So this estimate of sigma 2 is used instead of ms of the residual to produce an externally studentized residual. This externally studentized residual, we call it R student. So it's the R student because it comes from the studentized residual, right? The R student offers a more formal procedure for outlier detection by a hypothesis testing. So it's like the same as the studentized. We would use it for the for finding out the outlier, but it's a little more formal, especially when we are using hypothesis testing. So before talking about the testing for lack of fit, I want to tell you something about the residual. All of these residuals that I told you, like the 4 different ones, I'm going to ask you specifically, like I would say that, okay, So give me the R student for the residual, like, or use this method. If I don't tell you anything, you would just go with the residual, like the general equation that we have for the residual. But I would specify that, like, for example, what would be the standardized residual? So it would be clear, very clear what we are looking for. Okay, so the next thing is the testing for lack of fit. We talked about this before. It's like that we want to test our model for the lack of, we talked a little about the lack of fit error and pure error. So let's look at it. So sum of the square of the residual, the general sum of the square of the residual, it's equal to sum of the square of the pure error plus sum of the square of the lack of fit. Pure error comes from the replication, and we are going to learn about it later in next chapters. And lack of fit, it's coming from the model that we have. So basically, let's say, consider this model. When you look at the model, it's like that you have beta null plus beta 1x plus epsilon I, right? So if I remove one of these parameters, say that, let's say that we had like plus beta 1, beta 2, like beta 1 times beta 2, x2 as well, for example. If I were removing one of these parameters, then I would have the lack of fit. So we always say that lack of fit, it depends on the model, like lack of fit, the sum of the square of the lack of fit error, it depends on the model. The sum of the square of that we have for the pure error, it doesn't depend on the model. It's independent to the model because it comes from the replication, it's outside the model. But the lack of fit, it's like that. So let's look at it. We say that the residual that we would have, the general residual that we talked, it's what's equal to the y minus y estimate. And then we can write it down. Let's just add y bar to both parts, like the average of the y. So it's y minus y bar plus y bar minus y estimate, right? Then let's get the sum of the square of them. Add the, like, get the deviation. These are deviation, right? For each of these data points that we have. Let's get them and get the sum of the square. So this is the sum of the square of regression. This is the, sum of the square of the residual, the general residual. And this one is going to be the sum of the square of the pure error. And this is going to be sum of the square of the lack of fit. So sum of the square of the pure error that we have, it measures pure error. It measures the, like, you would need to have the replication to find out the pure error. It doesn't depend on the model at all in reality. And then, or for example, you will learn it later. We would have, sometimes we have center points. We add center points to our experiments. So those ones cause the pure error as well. But the lack of fit is the measures the lack of fit, and it's due to like lack of fitting. It's like that you're missing some parameters, like you would need more variables. You need to add more variables to have more parameters. Or you have your model, and when you compare it with the optimum model, another optimum model, you will see that, oh, you are missing some parameters. So then that's another case that we would have this lack of fit. You can look at the tutorial. We're going to work on these like lack of fit and these ones. You will see that we have in the tutorial or practice problem. Consider as a you can consider as a practice problem as well, right? So chapter 2, the title, like the file name is chapter 2, example 2 on linear regression model. And please review the materials that I told you. It's also an example. So this chapter we talked about, it was very short, like very quick. Quickly we passed that. So we talked about the different stages that we have, general regression models, the maximum likelihood, just quickly review that. Joint confidence region. Joint confidence region is very important. We're going to use it later. I'm going to go to the more details of it later. And the model diagnostics, so different types of the regression residuals that we consider. So the next chapter is going to be about the design of experiments. We're going to talk about the design of experiment, and we'll go to the single factor, multi-factor, which leads to the surface modeling. We need to know them because of the surface modeling. Yeah, that's all for now.